pesky quiz at the start. All right, I'll begin with a word of prayer. So, Dearly Father, we thank you for this day. Just pray you to encourage the students if they're not where they need to be yet, and just help us to all glorify you what we do, and just to prepare for the test, which is upcoming, Lord. In your name I pray, Lord Jesus. Amen. So what do you guys want to talk about? Anything?
Is the test on Monday?
Yep.
77 on the mission.
The test is on Tuesday. What's that?
77 on the mission.
77 on the mission? 77 or 78 on the mission?
79.
70. Oh. I should say this about the quiz you guys just took. In summary, number 1, the definition. Number 2, diverges by nth term test. Number 3, diverges because it's essentially the p equals 1 series. Number 4, that converges because it's the sum of 2 geometric series with radius 3/10 and 7/10 respectively. So that's the solution to that quiz there, which I will write out and post in Canvas here hopefully later today. You guys just asked me about everything in the kitchen sink. Which one was it? 77. Determine what n is needed for the error in Sn to be at most 0.001. So you've got Sn equal to the sum k equals 1 to n, 1 over k cubed, right? And you want to bound the error between the sum, which you don't know. You want it to be less than or equal to 0.001, right? 3 zeros? 3 zeros. So what's the tool you want to use here? You want to use the integral test estimation theorem, right? So look there, and that's how to do this one. Use integral test estimation theorem. Let's see if I remember. I'm trying to think of the right picture here. If our picture is like this, right? If this is the graph of the function, and let's see here. I can picture Sn 2 different ways, right? Like one way I could do would be like this. Here's A1, here's A2, here's A3, here's A4, here's A5, right? So if this is n, let's say, well, let's say that this is, so over here is, say this is n minus 1, this is n, right? So rats. This particular inequality just never sticks in my head. Give me a second here, I'll look it up. Otherwise I can write, listen, the thing is I can write down things that are true from this picture, but I'm looking for a very specific thing to write down. So I want to make sure I don't waste our time here, as our time is limited. So yeah, this is theorem 4.12. They use this projector. We've got it here for a reason, don't we? So, come on. So the integral from n plus 1 to infinity of f of x dx is less than Sn is less than or equal to, oh, not s, but s minus Sn rather. The integral from, what is it? From n to infinity of f of x dx. And you can see that from like looking at this kind of picture. So I don't know. Fine. So this really. So here I have the sum, oh, how to say this? I could do Sn minus a1 is what? It's less than or equal to the integral from 1 to n of f of x dx, right? That much is clear. But you can also draw another picture, right? You can draw like this. See that? And from that, if you look at the green boxes, right? You have that the integral from 1 to n is less than or equal to Sn. So, and then anyway, so if you, the thing you need for that is to kind of like extend this idea out to infinity and do a very similar idea. Or from this, you can get to this. Anyway, the point is, you don't have to derive this. This is given to you. This is a theorem in the notes, right? And so you can use this to estimate the error. Because, listen, so what you want to do is put f of x equal to what? 1 over x cubed, right? You put f of x equal to 1 over x cubed, then you can explicitly calculate this integral, and you can explicitly calculate this integral, right? What happens when you do that? Anybody done this? You got a function of n, right? So you got, let me say, I need some other letter. You got some like, well, let me just say you got stuff in n here, right? And then you got other stuff in n here, right? And you need to make that such that what? Such that these two things, right, are no more than this value. So hypothetically, suppose stuff in n worked out to n cubed over 7. It does not, but suppose it did, right? And suppose the other one worked out to minus n cubed over 7. It does not, but suppose it did, right? Then what would you have to do, hypothetically, if that's how that integral worked out? What you'd want to do is you'd want to take this and solve this inequality. 3 zeros, right? Listen, I did this for the p equals 2 series in the notes, right? If you look at, let's see here. Right, yeah, right here. See this? This one? So if we calculate n to infinity for 1 over x squared, it works out to 1 over n, right? So then to make the error, all I have to do is I want to bound the error by 1 over n. So I want 1 over n to be less than 0.1. I think on the other side you get 1 over n plus 1, so that one's fine. If it works for this side, we'll be fine for the other. But anyway, let's see here, and then like on the next page, I'm like, okay, so suppose you want the error to be, let's see here, what did I do? I guess I didn't ask, okay, so I admittedly I have not, it's not exactly like your homework problem, right? Because I'm just seeing what happens at 1,000, right? But understand that the mathematics here allows you to solve the, this, whatever that integral works out to, less than that value. And whatever n gives that to you, that one will suffice, right? If in doubt, go one more, right? It always improves as you go on out if it's convergent. So, does that make sense? Yeah.
Why do you need the n plus 1 interval? Because from n to infinity is all the stuff you haven't added yet, so that should be with the error.
I mean, I don't suppose you'd. So let's say it this way. This is the maximum error, and this is the minimum. Like the error has to be between this and that. So it's like all I have to do is look at this side really to be safe. This side over here tells me that my guess is not, extravagant, right? I mean, like, I could pick 1,000,000, when 1,000 will do. But if you look at this, then you can tell 1,000 works, whereas 9, it pins down where you have to make n. Because if I can solve this for 1n, I can solve it for well, I think it goes the other way. It's not going to be this, right? It's going to be like flip the script here, right? It's going to be like this, yeah? Good grief. It's more like that kind of inequality, right? I hope. If it's like the other way, then that's bad news because it's not going to work, right? So anyway, like I was just answering Sam, I think you're right. I think it's really just you can just focus on this piece right here because the other piece is just to make sure that you're making n as small as you can get away with, but no smaller. Did I ask the homework question in that way? I don't think I was that. I said what n is needed for the error to be at most. I guess anyway, if you solve this inequality carefully, then you'll get that n. Yeah.
So if your n's going to be like a really weird small number?
No, it's going to be a big number.
It's going to be a big number?
Yeah. Yeah. And you can, you guys live in a wonderful time where you can check your answer because you can use Wolfram Alpha to calculate the exact value of the series, and you can compare that to your choice of n, see if it actually worked or not. Yeah.
So in that inequality, are you just plugging in 0.0001 before that S minus S?
You are setting whatever this integral works out to here.
Yeah.
You're setting that. I would say set that equal to 0.0001. But you don't have to you could solve it, but all that's really required is that you find something that's an n that makes this this integral less than 0.001, right? As long as the integral is less than, so if I have this as less than 0.000, use your imagination, 1, then if this is less than that 0.0001, then so is that. So you could equate the integral with 0.00001, or you could solve it less than that. Either would do. Yeah.
So if you're going to do that, what does it matter to solve the integral and use the bounds n plus 1 to infinity?
Yeah, I think you don't necessarily need to do that, but you could check on the n plus 1 to make sure that your choice of n couldn't be improved, let's say. Yeah. So what was the other question you guys had about? Now 78 is way easier. Why is 78 way, way easier? What's the difference? This is 79, right? Wait a minute, 77? 77. 79, in contrast, 78 in contrast is the same thing, right? It looks like the same thing, but it's not quite, is it? What's the difference? Minus 1 to the k plus 1, isn't it? So there you have a what? You have an alternating series. How do you bound the error in the alternating series? Yeah, the alternating series estimation theorem says that the error between the sum and the nth partial sum is bounded by the next term. So you don't have to do the integral. You just have to look at the next term you're not using. So what is bn plus 1 here? In this case, it's just 1 over k plus 1 cubed, or 1 over n plus 1 cubed. So basically, you just have to solve. You can either do n or n plus 1, right? If I put an n here, what do I put over here? Right? So you could do that. Basically, you just need to look at how can I make 1 over n cubed less than or equal to what do I want? In this problem, again, it's the same thing, 0.001, right? And if I write much more, I'll have solved it. So problem 78 is way easier than problem 77. It's much, for me anyway, like when alternating series are very nice for estimation questions because the alternating series estimation theorem is Well, very simple. I put this into practice for the sine series we looked at the other day, right? So you can look at that example for an illustration of how to do this alternating thing. Other questions? Yeah.
Sorry, I'm still kind of confused with 78. How did you?
I haven't done it. I've just explained how you could do it. You have to integrate this to find a formula.
Sorry, 78.
Oh, 78, sorry. Yeah, my bad. So again, the alternating series estimation theorem says that the error in the nth term, or in this case, the error in the n minus 1th term, is bounded by the next term. So you just have to look at like the positive term. So the p equals, the alternating p equals C3 series. Here you have b sub k equals to 1 over k cubed in the language of the alternating series. So if you want the error to be less than 0.0001, you just need to like look at how do I make, 1 over something cubed to be less than, well, 1/10,000th, If I can find the n for that, then I found how many terms I need to take before the series converges to within 1/10,000th, I can't say 10,000th today, of the actual sum of the series.
So can it be like multiple numbers?
Well, I think there's a first number that works. And then anything after that will also work, because as you take further out, you're going to get closer and closer to the answer, right? Like we saw in the picture for the alternating harmonic series, right? It's like once I'm within 1/10 of the answer, everything past that will be also within 1/10. But I'm really asking what's the first one that works to make the question interesting. But in practice, I don't usually quibble too much if you guys got, like, if it works at 999, but you put 998, I'm usually sympathetic to that in terms of partial credit. Like, probably I'm not going to take points off at all, in all likelihood, so. Or if you put 1,000 when it should have been 999, I'm probably going to be like, Other questions?
Show us the
84, I can talk about it. Ah, okay. So this one I'll actually try to solve with you guys. Let's see if we can do it. Anybody get this one? Yeah. How did you get it?
You solve for the sum of its absolute value and just the sum of itself. The absolute value diverges with the convergence.
Okay, so you're like, so you just, in other words, I guess my question then is, all right, so let me dig down a little bit more. I mean, that is what you should do, correct? So to show that it's conditionally convergent means what? We need to show two things, right? It's not absolutely convergent, right? And also that it's convergent. If you have those two things together, then by definition that makes it conditionally convergent, right? So that's what we're trying to do. We're trying to show that this has those two things, right? So this is two problems in one, right? So let's see here. Let's start with the convergent. Can you tell me why this is convergent, guys? What's that? Because it's alternating. Now, is that enough? So this is an alternating.
Well, I want to change the chaos.
Right, with natural log of k over k is greater than 0 for k greater than or equal to 3, right? I probably could have started this thing at 2. It would have been also fine, right? 1 is definitely a problem, right? But I started it at 3. So it's positive. What else do we need to apply the alternating series test? More than that, what else do we need? It needs to be decreasing. Is it clear that the natural log of k over k is decreasing? I don't think it's clear. Because they're both going to infinity. Which one wins, right? What's that?
The denominator wins.
The denominator wins? How do you know?
Well, it's just, if you graph it, it's just
Ooh.
as it goes to infinity, it's increasing, and then the natural log of k is increasing, but logarithmically, so it kind of drops off.
Right. How could we, I mean, I think you're right, but how can we be sure about that? Take the derivative, right. So if we, let f of x equal to log x over x, then f prime of x is, what is it? It looks like a minus 1 over x squared log x plus 1 over x squared, which is 1 over x squared times 1 minus log x, right? And if x is larger than 3, the natural log of x is what? It's larger than 1, right? Maybe that's why I put the 3 here, just to make this less awkward. So this is definitely less than 0 for x greater than 3. Therefore, f of k, which is equal to b sub k, is decreasing. That's, okay, so we've got the terms are positive, they're decreasing. What else is required? To apply the alternating series test. What's the limit as k goes to infinity of b sub k? It's 0. Why is it 0 though? It's not clear yet, is it? Yeah, we should do L'Hopital's rule, right? So apply L'Hopital's rule, extending k continuously. So L'Hopital's, it's infinity over infinity. That's the type. We've got limit. This building's got indigestion or something. What's going on in here? 1 over k over 1. And indeed, that limits to 0. All right. And here I extended k continuously. So much writing. All right. Yep.
So do you have to say all this?
Yes. Yes, this is the solution. So now, what if you don't say all this? What if you just summarize this on a test? Will you still get partial credit? Yes, you'll get a lot of partial credit. Will you lose something? Possibly. Kind of depends. But this is the full solution here. And still not done, right? Conclusion, thus, the sum, k equals 3 to infinity of minus 1 to the k, log k over k, converges by what? Alternating series test. You can use abbreviations, right? Alternating series test, direct comparison test, limit comparison test. We have abbreviations for these, right? You could give the series a name and refer to it. I've done that a lot, right? Like I've called this Bob or Jane or something and referred to it like that. Okay, at this point, we've just done half the problem. We've showed it's convergent. Now, Sam at the start said he took the absolute value of it. Why did you do that? How do you show something's not absolutely convergent? What do you have to do? Right. So let me work over here for that one. So we're looking at the sum. What was it? It was is it log k over k? I can't remember. Log k over k. That's the absolute value of the series, right? Right. So here is the absolute value of the series. Right. If we take absolute value minus 1 to the, what was it? Minus 1 to the k. Well, that's that goes away, right? I mean, fine. The absolute value of the whole thing. The bottom line is that the absolute value kills the minus 1 factor, right? And you're just up against this. Now, how should you do this one? Converge or diverge. Like, I look at it and I go, ooh, diverge because this is worse. It's worse than the p equals 1 series, right? If we just had division by k, we'd already be up a creek. But with the multiplication by log, which is getting large in the numerator, that just makes it worse, right? So this is definitely divergent. How do we show that? What's that? The what test? Integral test? You think you can integrate that? I think you can. Let's see here. So, just messing with you. But yeah, I think you could do integral test. Integral from, let's say, 3 to infinity of log x dx over x. You could do that, I think. That's a hassle, though, because, again, although we've already done the work over there, we showed that it's decreasing. Right? We showed f of x is what? Positive decreasing with limit 0. So I guess, hey, why don't we do the integral test? We've already done the legwork for it anyway, right? So this is the limit as t goes to infinity of the integral from 3 to t of log x dx over x, which is what? The limit t goes to infinity of what? Sidebar, what's this integral? Is that not du over u, where u equals to, excuse me, it's not that, is it? U du. Yeah, thank you. U du. U is log x. So 1/2 u squared plus a constant. Let me get to the point here. So the integral is 1/2 the natural log of t quantity squared minus 1/2 the natural log of 3 quantity squared, right? And that is not, there's no ambiguity here. This one just blows up, right? So if I had Matthew here today, I could just say, Matthew, what's the answer? And he would give the only answer that I've programmed him to give, which is divergent. So there we go. So I was trying to program him to do divergent and convergent, but I couldn't quite. He wasn't on board. I was like, I was going to try to make him. If I asked him what mom said, then he would say convergent, and then if I said what you said, he'd say divergent. That if I could have done that, I felt like it would have been a little bit more impressive, right? If I had been having him give 2 different answers at different places, I would have achieved something. But oh well. So then it diverges by the integral test, right? Let me give this a name, Bob. Thus Bob diverges by integral test. Thus, I'm tired of writing this stupid thing. Pac-Man. Thus, Pac-Man is not absolutely convergent. Hence, Pac-Man is conditionally convergent. So you're like, do I have to say that last sentence? Yeah, I think you do. That's part of the solution. Like, complete the thought, right? Don't make me complete the thought for you. You complete the thought. Yeah?
So to prove something is absolutely convergent, we would have to take the absolute value.
Yes, yeah, right, yeah. So like, yeah, to say something's absolutely convergent means that the series formed by taking the absolute value term by term, that corresponding series of positive terms converges. That's the definition of absolutely convergent. Other questions, guys? Yeah. Say,
Is there a chance we can just say that because ln is always going to be, it's always going to produce a result smaller than the initial value we inputted? Can we just say that? Because it's a natural log, and the natural log is going to always output something less than the input value.
I would prefer you show the derivative is negative for this problem. I mean, debatable, like maybe if you wrote the whole sentence out, but there exists some chance that you'd be arguing with me about the grading after it's all said and done. I mean, I'd probably give you your points back, but I think there are definitely examples where we can all agree it's decreasing. We don't need to show work, right? Like, for example, if I have something like -1 to the, n plus 1 over k squared, k squared, listen to me, I can't get my n's and k's all mixed up. Like this one, right? Okay, I think it's just reasonable to say, okay, b sub n is 1 over n squared. 1 over n squared is decreasing as n increases. I mean, this is just, there's no real debate about that, right? You have 1 over something that's clearly getting larger as n increases. It's clearly a decreasing sequence there of positive terms. Here, there's some kind of give and take between the log and the k, and that's why I feel like calculus is kind of more appropriate here to show it's decreasing. Now, what you said is totally reasonable, like the fact that log, basically your argument is that log k is less than k, thus, right? And then something like that, and then you're building from that. So log k plus 1 is what?
Log k plus 1 over k plus 1 is less than
Log k plus 1 over what?
over k plus 1
Uh-huh.
is less than log k over
Yes. Yes, if you wrote that out, then I'd be inclined to agree with you. But I would also point out that that's harder than taking a derivative and seeing the derivative as negative. I think it's harder. Am I wrong? If I'm wrong, it's because you have a better intuition for inequalities than I do, which is totally possible, right? Totally possible. My strength is not inequalities. Ah, but we should all be able to differentiate, yes. Of course, differentiating alone is not enough, right? To make the derivative useful, what did I have to do? I had to do this algebra step, didn't I? Without that algebra step, you can't really see from the derivative that it says what it says either, can you? Listen, so guys, if you're lost, you know it's alternating, but you're just not sure that you've proved it's decreasing, then punt, right? Say something that seems reasonable, and hopefully I won't notice, right? Maybe I'll just be happy that you recognize it's alternating and that you've satisfied the conditions. And listen, we're talking about a second order consideration, right? A justification of a justification. So it's, whatever. Let's go on to other problems, yeah?
So they're saying alternating, that's just because negative 1k outcome?
Yes, pretty much anytime you got a -1 to the k or -1 to the n, that's going to give you plus minus, which is going to make it an alternating series. There's another way to disguise this, of course. Popular alternative choice is this, pi n, right? Cosine pi n is another way to make it alternating, because cosine pi n is actually equal to -1 to the n in disguise. So. Okay, other questions, guys? Let's try to get more done today here. Where did I put my phone? Oh, thank you. The good Saint Nick has helped me. Let's see here.
Oh, man. Oh, gosh. Not another nickname.
Nickname.
Well, you said Nichols like the first couple classes, and now it's. Oh, I get what you did there. Nickname. Okay. All right. Never mind. They call me Nichols like every day now since you did that one.
I think you can't help but have a nickname. I mean, your name is Nick, so.
It's Taylor, but we'll go with it. Oh yeah.
It could be worse. Let's see.
It could be a lucky nickname. Could call you Don. Ooh. Don.
Let's see here. Other questions? Yeah.
For 70, it says that 2 to the n over n factorial was less than or equal to 4 over n over n. I need to calculate.
Problem 70. Mm-hmm. Well, how would that help you calculate that limit, if you could show that?
Because before the n's over anything at 0, I put 2 to the n over n factorial. N factorial is going to increase at a faster rate than n.
Uh-huh.
And then 2 to the n.
But, all right, so how would, so let's suppose we have showed this, and we can talk about that in a minute here, but let me just kind of get to the end of the problem before we do the start, right? Suppose we've already shown this, all right? I'm not saying we have. What else can you add here to the mix? What goes below 2 to the n over n factorial? 0, right. And so then you have this squeezed between this and this. Then you can use the squeeze theorem to show that the limit exists and is equal to what? 0. Right. So if you establish this inequality, then it's easy to use the squeeze theorem to calculate this limit. That's the idea here. So how do you establish this inequality? What is 2 to the n over n factorial equal to, manifestly? 2 times 2 times 2. 2 of those, right? n minus 1, n minus 2, 3 times 2 times 1, right? Well, I guess first of all, is that inequality true for n equals to 1? Just as a kind of double check on our thinking. Is this true for n equals to 1? Yeah, it's true. Even if it wasn't, we could still use the squeeze theorem, right? Actually, you just need the squeeze theorem for n sufficiently large. We could still make the argument, right? It does so happen to be true for n equals to 1 to infinity, though. I don't know, like, I think if we just keep, let's see here. Let's suppose n is greater than or equal to 2. All right, because we've already seen n equals to 1 works, right? Then what can you say about 2 over n minus 1? If n is greater than or equal to 2, what can we say about 2 over n minus 1? Can we say anything? I don't know. N is greater than or equal to 2. That means n minus 1 is what? Greater than or equal to what? 1, right? True? I'd like to make the numerator what? If I want to make something larger, I do what? Make the numerator smaller, right? So this is less than or equal to 2 over 1, yeah? Because I replaced n minus 1 with something smaller. So I made the fraction larger, yeah? But what about like n minus 2? It's what? Well, anyway, if so I've just argued, yep.
You could make a ratio of those two fractions. Less than or
Maybe. But my point is that this is 2 over n. This one right here, right? I can replace with 1, right? Then I've got 2 over n minus 2. 2 over n minus 3, yeah? 2 over 2. What can you say about all these fractions, given, n is greater than or equal to 2. Ooh, n equals to 2 is problematic there, isn't it? Well, excuse me, if n, if n is equal to 2, then this isn't here, right? If n is equal to 2, this expression is just 2 times 2 over n times n minus 1, right? Excuse me. This is just this, right? So I have to have the proper interpretation, right? Like, if I'm writing all this, then it already means that we're large enough that we don't have division by 0 in there. Anyway, my larger point is that these are what? Let me put it more specifically, like rats. So I would say that their fractions are all large. You can replace those with 1, right? Because, like, for example, n equals to 3. You've got 2/3 here, and that's the end of the line, right? If you're at n equals to 3, this isn't here. You know, this is it, right? At n equals to 4, it looks like that, right? So those fractions are less than 1 for n larger than 2. Which means what? If those fractions are smaller than 1, you can replace them with what? Which is what you want. Now, if you don't find this convincing, I think you could probably prove this by induction more convincingly. Like, that'd be another way to do it. Whatever Sam was talking about in terms of ratios, that might be another way. I mean, there's more than one way. If you don't find my particular presentation of this convincing, fine. But other questions? Here's the induction proof. Given 2 to the n over n factorial is less than or equal to 4 over n, consider 2 to the n plus 1 over n plus 1 factorial. Well, that would be 2 times 2 to the n over n plus 1 times n factorial, which is less than or equal to 2 times 4 over n plus 1 times n by the induction hypothesis. Which is less than 4 over n plus 1 for n greater than or equal to 2. Therefore, since n implies n plus 1, it's true by mathematical induction. I've assumed that the inequality holds for n. I have shown that for n greater than or equal to 2, it's pretty clear that 2 over n is a fraction that's less than or equal to 1. We can agree, right? So I replaced this 2 over n with a 2. I kept the 4 in the n plus 1. Now I've now showed that this is less than that. This is exactly the claim with n replaced with n plus 1. Therefore, the inequality holds for all n. Since it held for n equals to 1 and n implies n plus 1, this is called proof by mathematical induction. If you get lost in the weeds of like the symbols and what it means, this is sometimes a better way to do things. But anyway, I don't require I don't require you to prove things by induction in here, obviously. Like that's not part of like the usual required part of this course, but I mention it because it is sometimes helpful, even as a calculational method. So, you guys have other questions? Let's go to them. Yep. Number 90. I got to be careful. If I'm not careful, I'm put all my problems out of order. Then I'll be in trouble. Problem 90. Oh. The funny thing is this one's actually easier than like a lot of the other problems we've talked about today, but it looks horrible, doesn't it? So oh, okay, so thank you for asking about this. Typo. AN equals to SN. Rather, AN goes to SN. So let's interpret this problem as SN equals to the sum k equals 1 to n of 1. See, this is something I learned this semester, guys. This way of looking at this problem. And so, all right, that's the way I have to interpret this. And I'll explain more as we go on here. But basically, the idea is to look at this. This is the Riemann sum of some integral. Right, what is the Riemann sum? The Riemann sum, remember, integral from a to b, f of x dx equals limit as n goes to infinity of the sum k equals 1 to n of f of x star, well, x, let's just say x sub k delta x, right? Where you have a is equal to x sub naught, x1 is equal to like a plus k delta x, da 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 da. Eventually you get to xn is equal to b. The delta x is b minus a over k in this context. N rather, my bad, n. All right. So in order to put this into practice, you've got to make some choices, right? Like, what's my delta x, and what's the function I'm looking at? It's fairly clear that the function I'm looking at for this one is either x to the fourth, or maybe 1 plus x to the fourth, right? I think if we do 1 plus x to the fourth, it's easier. Listen, there's not a unique way to do this, because a given partial sum like this could be the partial sum for like a lot of different integrals, actually. What I'm trying to get at here more, though, is what pops up here I would identify as the nth partial sum of a series. That's the pattern. I was thinking when I wrote the homework that it was a sub n, which is just not the right way of thinking of it at all. And so you guys tell me, what's a good, I mean, you got to make some choices, right? But my choice would be that this is my delta x, right? And I personally love integrating from 0. So I'm going to make a equals to 0. That's just simpler to think about. If you make the starting point of the integral 0. So my delta x is, you know, like b minus a over n. But that's just going to be b over n, because I'm going to make a equals to 0, my choice. And I would encourage it to be your choice. If I do that, what's b equal to? 3, right? So we're looking at the limit as n goes to infinity of Sn apparently being the integral from 0 to 3 of something. If I do that, what's this 3? What's 3k over n equal to? This is equal to k times delta x, right? That is what I would call x sub k if we're using the right endpoint rule, and let's do that. So this, in view of these identifications, becomes the sum k equals 1 to n of 1 plus x sub k to the 4th power times delta x, right? So if we pass to the limit as n goes to infinity, we obtain the integral from 0 to 3 of 1 plus x to the fourth, not the parentheses x to the fourth, right? dx. And you guys can do that integral. And since you can do that integral, you've calculated this infinite series. Would you like to know a nasty question? A nasty question to ask you is, what is a sub n here? In other words, you know, this is a series, right? The question is, this is the sum k equals 1 to infinity of a sub k. What's a sub k? That is actually a very difficult question. I added a page in the notes where I worked this out for a more simple integral, though, if you're interested. So, but we should focus on the majors, not the minors in here today. So other questions?
Problem 69.
Uh-huh.
Is it n equal to 1 or k equals to 1?
Ooh, that sounds like a good question. Oh, that's supposed to be k equals to 1. Thank you. All right, so I know some of you are probably scrambling to finish all these problems for tomorrow, if I had to guess. So let's talk about some of these problems. Let's see if I can find one that's... Actually, that 69 might be a good one to talk about. Yep. Here you're up against k squared over 2k plus 1 factorial, right? So what should you do there? What's that? You said that was a trick question? No, it's not like that. No, I try not to do that. Although I have, Dr. Skibordis told me, I think on a Calc 2 test about 10 years ago, he said, he says x equals to 5. What can you say about x? And they couldn't do anything. So I'm not sure what they mean. I mean, what do you do if you have a test and the professor tells you x equals to 5? What can you say about x? I mean, I would hope you just say, well, x equals to 5. You just told me. What do you want from me? It's a real number. It's a rational number. It's a complex number. These things are all true. What more? I don't know. He just wanted them to say back that x is a real number and it's 5, something like that. The wording might have been slightly different, but it was essentially this. So I try not to ask those kind of questions because I don't like the results. Oh yes. You guys remind me, what was it, 2k or k squared? Which is upstairs? Over 2k plus 1 factorial. Listen, guys, I'm tired of writing k at the moment, so if it's okay with you, I'm going to switch that to an n. In fact, as a point of order, I think I need to go edit my notes and change all my k's to n's, because the k is really annoying to write for me. And you guys accuse me of my k being n anyway, so why don't I just accept my fate and use n? It's my own fault. Yeah, it is my own fault. What's the right tool for this problem? Ratio test, right. This is definitely ratio test. So call this thing a sub n, right? We want to calculate what's the ratio of n plus 1 over an. All right, let's do that. So this is n plus 1 squared divided by twice n plus 1, right? Plus 1 factorial times what? Times the reciprocal, which is 2n plus 1 factorial divided by n squared. Now, how does this work out here? This is actually what? That's 2n plus 3, isn't it? I have 2n plus 2 plus 1, which is 2n plus 3. So the way to do that is we have 2n plus 3 times 2n plus 2 right? Times 2n plus 1 factorial. And upstairs we've got n plus 1 squared. So if you guys are wondering what I did, whenever I'm doing division for this kind of problem, I multiply by the reciprocal as to make my life easier. So this is the property of the factorial, right? It's defined recursively. So if you're up against a factorial, look to cancel the factorial with a factorial as a general point of order. Like, you know, that's so see? And what happens with the 1 over n squared? So these two guys give me a 1 plus 1 over n squared. All right. Then what? So n goes to infinity, what happens here? The top goes to 1, the bottom goes to huge, goes to 0. Therefore, that's rho less than 1, right? So this is my rho, less than 1, so ratio test says Mario converges. There we go. Yes, it's me, Mario. Yes, very good, very good. Yep.
When you're using the ratio test, do you need to use rho or can you use like L or something?
Well, I called it rho, but you could call it L if you wanted to. Just as long as you say the words ratio test, I'll be happy. Problem 68 is a telescoping series, right? Problem 70 we talked about. Problem 71, you need to think through, all right? I'll leave it at that. There's no series or convergence there, right? That's just a problem to try to make you think about how do we rewrite sums, how do we make substitutions for sums. Problem 72, partial fractions. You can do partial fractions on this, and if you do that, it will give you that this is a telescoping series. Some of you didn't notice that, and you've already showed it converges. Good for you, but you can calculate this one some, because it is telescoping. But you're right, I mean, this one, so I guess that's the other danger to watch out for, like on the test going forward. I have questions where I'll say, you know, converge or diverge, if possible, calculate the sum. So this would fall into the category of it's possible to calculate the sum. Now, and I did say calculate here, so that does kind of imply, you know, find the value. It's not hard though. You just do partial fractions, you calculate the nth partial sum, take the limit, you'll see what it's equal to pretty fast. It's not that hard. But if you're just interested in convergence and divergence, you could do what? You could do limit comparison with p equals to 2. You could do a direct comparison argument. There's lots of ways to solve this problem otherwise, problem 72. Yes, sir?
The only way to calculate like the actual partial sum is through like a geometric series of telescoping?
It's either geometric telescoping or this thing. There are other ways. We learn after test 2. Problem 73, there are different ways to go here. Certainly integral test is possible, right? Because it can integrate inverse tangent over you know, x squared plus 1 is a u substitution. U equals inverse tangent substitution. Problem 74, you can prove that that converges any number of ways, right? Direct comparison, limit comparison, a few different ways you could do that. Problem 75, I would go with a direct comparison for this problem. Because